Alright guys, within this video we're going to look into section 4.4, which is talking about modeling and optimization within calculus. Now we're not going to spend a whole lot of time in this section, but we're going to utilize it in a way just to kind of further prove how calculus is used in real life circumstances, and it's not just a bunch of gibberish that we give you. So our goals for this video is to use topics of calculus to show real life applications, specifically talking about how to maximize profit and minimize average cost, okay? So the reason why I want to look into this is, one, at some point in your scholastic careers, everyone's going to have to take in some kind of economics course, and so this will kind of give you a little bit of an insight into economics if you have not taken it already. But I think it's also something that maybe a lot of more people are more interested in. I mean, for the most part, I think most people are, more interested in terms of finances versus, using volume of a box or something of the nature like that. And so let's take a dive into this this concept here. So we're going to look at the concept of maximizing profit. All right. Before we do so, I want to kind of show a graph that's going to kind of put some things into perspective. What you see here now, guys, is a quick scenario. Suppose we let the function r of x equal the revenue from selling a particular x item. And then you're going to let c of x equal the cost of producing said item. And then you're going to let p of x equal the profit from selling the item, which is the same thing as the revenue minus the total cost, okay? So what we really want to look into is, like I said, a little graph as to what does this all actually mean and how does it all kind of come to fruition as well. So let's say, for instance, I have a cost graph that I'm going to put in red. And so let's say I have a cost graph that looks something of the nature like this. So this is my c of x function. And let's say I have a profit, or excuse me, not a profit, but a revenue graph that looks something more like that. So there is my revenue graph. And so, I think a mistake that a lot of people make when they're dealing with, finances and just, owning their own small business, it's like, hey, the more product I make, the more money I can make in the end. Now, that's not always entirely the case. And in most cases, it's actually not. Most companies have to find a spot where you find the producing a certain amount of product will always yield the highest return in terms of profit when it's all said and done. Because think about what's happening here on these particular graphs. These points in which the cost and the revenue are intersecting with each other. Think for a second as to what is really happening at these 2 points of intersection. Hopefully you kind of understand the fact that when they intersect, that means that you are just breaking even. And no business just wants to break even because you're not going to make a living, obviously, doing that. So this is just really a break even point. And that's, I guess great if you want to get your money back, but most businesses, that's not what their goal is. And so we need to find the spot into where are we going to find the biggest profit, the most maximum profit that we can get. And so what we really need to see is we need to see where the slope of a tangent line or the derivative is showing increase for both the cost and the revenue, but specifically that it's showing an increase that is equal to each other. So let's think here for a second. The distance between cost and revenue. So I'm going to kind of use two spots on the graph to show. The distance right here and the distance between here. Think about it for a second. Does the bigger distance between the green and the red graphs, the cost versus revenue graphs, does the bigger distance show more profit or less profit? Hopefully you can see that the bigger distance shows more profit, because if your cost is less than your revenue, then you are maximizing profit. We'll see what's happening here. I'm going to highlight it. When your revenue in green that I'm highlighting is greater than your cost, you are seeing maximum profit. But on the other side of things, when in this case your cost, which I'm highlighting right now, is greater than your revenue, you are seeing a loss. You don't want your cost to be more than your revenue because then you are losing money in the end. And so this spot right here in which the tangent lines are equal to each other, this will give us max profit. And in this case, where these tangent lines are equal to each other, this is going to get us a max loss. And that's bad. We don't want that loss in there. So that's going to give us our max loss. So we need to find that point in which the slopes of the tangent lines are equal to each other in such a way that at the point of the graph, the revenue is greater than the cost. And that's going to kind of lead us into our theorem. And what we're really kind of looking into is what do the derivatives of each of these R, C, and P functions mean? Well, the derivative of R, our revenue with respects to X, is what's called our marginal revenue. The derivative with respects to C, of C with respects to X, is what is called our marginal cost. Hopefully there's some familiar terms, especially if you've taken calculus. And then the derivative of P, our profit, with respects to S, is called our marginal profit. And so it's all super important stuff to know, especially if you're looking to get into business administration, anything with entrepreneurship, and things of the nature as well too. And so what we can kind of take from here is that our maximum profit occurs at a certain production level at which the marginal revenue equals the marginal cost, right? So not that the function itself equals each other, but that specifically the derivative or the slope of the tangent line equals each other. So what this really puts into perspective is that max profit happens when the derivative or the slope of the tangent line for the revenue is equal to the derivative or the slope of the tangent line of your cost, right? And so this is going to show us specifically that we will find some maximum profit. So let's look into an example here as to how we can specifically go into maximum profit. So let's suppose that R of X is equal to 9X and C of X is equal to X cubed minus 6X squared plus 15X, where X represents thousands of units. X is thousands of units, okay? The question says, is there a production level? So is there a spot in which the revenue and the cost match up so that it maximizes profit? And if so, where? So where are we going to find this out? So let's first and foremost, we know that in order for this to happen, we have to have the marginal revenue and the marginal cost equal each other. Or in other terms, the derivative of revenue and the derivative of cost equal each other. So let's find out what the derivative of each of these first and foremost are. R prime of X, well, if R was 9X, the derivative is going to be 9. And then C prime of X is going to be 3X squared minus 12X and then plus 15, right? So just multiplying down using our power rule that we've been dealing with. And so I need to know basically, hey, where are they going to equal each other? So set them equal to each other. I need to know what the x value in terms of units is going to be when these two equal each other. So 3x squared minus 12x plus 15 equals 9. I'm going to set it equal to 0 so I can find what those values of x are in fact going to be. So let's go ahead and do that. So we have 3x squared minus 12x, 15 minus 9 gives us 6. So this is what we're going to be solving for. Unfortunately, this is not something that we can just factor out nicely, but we can use our quadratic formula to solve for x. So don't forget opposite b. So x is going to equal opposite b plus or minus the square root of negative 12 squared minus 4 times a, which is 3, times c, which is 6, all over 2 times a. And so this is going to give us our two values. Now, we all can easily substitute, finish this problem on out. So to save some time here, the values for x in this case are roughly going to be, I should put approximately, 0.586 and 3.414. Okay, so these are the two values for x in which this is going to happen. So the possible production levels for maximum profit are going to happen at x being approximately 0.586, or it could possibly happen at 3.414 units, okay? Now, what you would just basically have to do is to kind of determine more so in terms of a specific a value here, maybe on their graph. You want to graph it and see exactly where that happens. So let's graph real quick. If you do on your graphing calculator, the graph looks something like this. So we've got our x and our y values. So let's take our cubic function, which shows our cost. So our cubic function was represented something of this, and then we have 9x being our particular function for revenue. So it went somewhere in the matter of this. So we just basically had to see where do we see maximum profit versus maximum cost. So basically, where on the graph is the revenue going to be higher than the cost? Well, that's going to be happening right in this area where the revenue is higher than the cost, because remember, this was R of x and this was C of x. This part in which it is lower, all right, this is going to show our loss, and this is going to show our profit, or our max profit that we see right in there. So just kind of knowing between the two, it's going to be happening. This is going to have to be smaller. So this is happening at 0.586, and this is happening at 3.414. So we find our maximum loss. We find our maximum loss at 0.586 thousand units, and we find our maximum profit at 3.414. So max loss at 0.586 thousand units and max profit at 3.414 thousand units. All right, so it gives you a little bit of an insight into utilizing maximum profit here. What I want you guys to do is to give a shot to number 23 in your book. So number 23 on page 228. Give it a shot. It is an odd number, so the answers are in the back of the book for that, and see what you can come up with in this particular case.